synthesis, natural product libraries, a lot of it. They get lots of it, and then they use eventually so-called high throughput methods to discover the lead molecule. There is therefore a need of a fast, cost-effective, mechanism-based screening method for lead discovery and optimization. There is a need of it. Unfortunately, it is not so obvious. It's not so available. Okay. This is the classical theory of drug development, the classical lock and key model. Lock and key model, which has gone through a several cycle of revision, but it primarily essentially is a complementarity in the structure of a ligand molecule and a receptor. Complementarity, समझते हैं ना? Complementarity, complementarity primarily means that the structural features which complement each other and they function as a lock and key. It is a very stereospecific because the amino acids which are actually involved, they have a different conformation. The whole molecular structure of the receptor, in this case enzyme, has a conformation, stereospecific, lots of electrostatic interaction, hydrogen bonding, hydrophobic interaction, so-called pi bonding, pi stackings, deuterining interaction, lots of non-covalent interaction, van der Waals interaction, but complementarity of structure is primarily responsible of it. And if I tell you that this substrate or so-called ligand actually bind into the active site here through a non-covalent interaction, that is your binding mode and binding affinity. How strongly it is binding and where it is binding is called binding mode and binding affinity respectively. Now, high throughput screening, traditional method of lead discovery, very large number of compounds are screened against a defined target. Technologies are used for this purpose. Very, very expensive technologies are used. People use robotics, people use high throughput screening, biosieve machines. There are millions of dollars which people have spent. People are spending on the identification of lead molecule in an automatic fashion. Okay, so this is one of the reason why drug development is so expensive, because people are using non-validated technologies. Now, I want to take you to a different type of high throughput screening, and this is an exciting opportunity. People have been working since the first paper in Science was published in 1996 on using NMR spectroscopy for drug discovery. And then there was an issue of angioventosomy. Please go and check it. Uske title page ke par hi there is a big funnel, and on top of the funnel there are thousands of compounds, and NMR is used as funneling device in which you eventually get one or two molecules down the funnel. So it's an interesting issue, very, very important. There are 3 articles in that issue which are extremely relevant of the use of NMR in drug discovery and development. It's now used for the screening of libraries of compound for weak to tight binding with the receptor target to आपका enzyme in a high throughput manner. And this high throughput manner is the need of the time, because you want to save time in the discovery of lead molecule. It is quantitative in nature. So precisely as biophysical method in which you determine the IC50 values, you can also determine the binding affinity by using NMR spectroscopy. And there are various methods and pulse sequences have been developed for the initial screening of lead compounds. The process is more efficient. Less number of compounds are required, and I want to take you to several methods. Let's start with a process called fragment-based method, in which we screen fragments for their binding affinity against a defined target. fragments are generally very small molecule, 9 to 10 atom K. For example, what are the fragments of wind blasting? What are the fragments? The fragments of wind blasting are indole, clevamine, and certain functionalities. What are the component of salicylic acid? क्या है? And a benzene and okay, so there are small fragments, 9 to 10 atoms, non-hydrogen atoms. You don't count hydrogen in it, and you take these small molecules and you place these small molecule in a mixture which has your receptor, so-called target. And these fragments may have a weak but efficient binding affinity, high binding energy per atoms. And I want to show you how it actually happened. Okay, I invite you to think about it. This is your protein. Nazar aa raha hai? This is your protein, and you have two different fragments. This blue and this rectangle of red. This is ovoids, and this is rectangle. And you discover that this molecule, this particular fragment, has the affinity to a part of the binding site, active site of the enzyme. And you also, by using another experiment or the same experiment, you discover that this red fragment, which is something different, has the affinity with the binding site also. Now the only thing which you need to do is to link them together. You make a molecule composed of these two components, linking them with a carbon chain or anything else, appropriate distance. And when you create a molecule like this is called lead optimization, and you have identified a new inhibitor of the enzyme, right? Extremely interesting. And if I tell you that I would like to put with my protein several fragments, and I would like to identify out of which fragments 2 or 3 are binding with the active sites. And once I identify these fragments, I link them together by using a conventional chemical method and create a new inhibitor, optimized lead molecule, which has the capacity of binding with the active site. Now, this is very, very contradictory to a high throughput screening, because in high throughput screening, you have whole molecules, and you try them one after the other for a long period of time to identify a lead molecule. In this particular type of fragment-based discovery, you have only the fragments, the essential fragments of organic molecule. क्या होते हैं essential fragments of organic molecule? Remember, these are small molecular chemistry. Remember that 90% of the drugs in marketplace has a molecular weight of less than 500. The drug discovery and development, except biological, is just a small molecular chemistry. So it is a question of a small molecular chemistry, and in small molecular chemistry, what are the components? You would have a benzene, you would have a lactame, or you would have a lactone, you would have a carboxylic group, you would probably have some ether group, a tetrahydrofuran, something like this. These are the basic constituents. These are the fragments which make organic molecule, which are the drug-like character. And remember, a long time ago, if you remember, I discussed with you extensively the Lipinski rule of 5, druggability. What are the essential requirement of a molecule? So-called molecular size, butanol, water interaction, hydrogen bonding capacity, hydrogen bonding accepting capacity, rotation of the double bond. All these are druggability character. which make them susceptible to bind with the active site of the enzyme. So therefore, these are the common fragments, and I would just throw 9-10 different fragments together, eventually identify 2 or 3 of them, and link them together. Link them together by using my own understanding of the chemistry. So what I would do, for instance, if I have this problem, I would measure the distance between 2 components of the active site. The active site has an interesting structure, and I would know precisely that the distance between this component and this part and this part is, let's say, about 5 angstrom. 5 angstrom means that I would have something like 4 carbon in between. Each carbon-carbon bond is 1.54 angstrom. And if it is 1.45 angstrom, it is about 3 or 4 carbon, which would give me a molecule which has 2 fragments with the capacity of binding with the active site. Now, how would I know that these fragments are binding? That is done by NMR spectroscopy. So let me take you back. There are 2 different types of techniques which are actually used in fragment-based drug discovery. Is a very, very exciting field. One is target or receptor-based screening. Remember, target and receptors are same. They are large biomolecule, enzyme, hormone or others. They are, or even viruses. I have seen recently a paper in which people have actually used STD against a virus. The whole virus particle can be X-rayed. You can have a structure of a virus molecule because it is a so-called, क्या कहते हैं उसे, organic molecule है. Virus is just a molecule. So the whole virus, the structures of lots of viruses have been determined by using X-ray crystallography, not by NMR, because NMR is so far not capable of going to the virus structure. Virus structures are fairly big, and in X-ray crystallography there is no issue of a size of the molecule. You can have as big as molecule, unless you're getting a perfect crystal, you will be able to get a complete structure. So even for the viruses, target, receptor, hormone, enzyme, viruses, you carry out a screening. Ligand, question is always asked, does ligand, which is your small molecule, interact with the target by following the changes in the chemical shift of target proton? So what you do, that you have a target, you record the NMR of a target, and then you add a ligand or several ligands, and then you see the changes in the chemical shift of the protons of the target. Target में क्या फर्क पड़ रहा है? Remember, ये chemical shift की change क्यों होती है? What make the chemical shift changes? Absolutely, electronic environment. And what changed the intensity in NMR spectroscopy other than polarization transfer? NOE, right? So the chemical shift change primarily means that there is a molecule which is interacting and changing the electronic environment, right? And the intensity, so this is one technique. And you observe and compare the chemical shifts of targets in the absence and presence of a ligand. In the absence and presence of a ligand, you monitor the chemical shifts of target molecule. And if there is a change in chemical shift, that primarily means that your ligand is interacting with the target molecule. If there is no change, there is no interaction. Remember, change can only take place when they are close enough to affect the electronic environment. If they are not close enough, there would be no change in chemical shift. There would be no change in chemical shift. Kindly remember. So it is the no, but I can tell you, for example, if you have a greater chemical shift change, that means that molecule is either more closer or has a functionality which affect the chemical shift. For instance, aromatic ring. Aromatic ring shield the proton or de-shield the proton depending on the region where the protons are lying. So this is the philosophy. The second philosophy is ligand-based screening. Ligand is interacting with the target, and how do we know? By observing the changes in the NMR chemical shift of ligand after the addition of the target. So essentially the same. In one technique you have a receptor, you're observing the receptor, and in the other technique you're observing the ligand. Now I would ask you which technique would be more suitable for initial screening. Which technique would be more suitable for initial screening? Initial screening, you want to identify the ligands, not the target. Target you already know. The only thing which you want to know that which particular ligands are capable of binding with the target. So for initial screening, ligand. For structure activity relationship in which you have a target selected and you want to know how closely it is binding, and then you're optimizing the structure, changing changing acid into esters or whatever you're doing, you would use this particular techniques. The first target receptor based screening is called SAR by NMR, structure activity relationship by NMR spectroscopy, and it is used for the second phase of optimization. Okay, this ligand based screening is a high throughput screening for ligand, because if you would have several ligands, the one which are affected are the one which are binding, right? Very simple. So if you have 1000 ligands, and if you see one or two of them are suffering from a chemical shift change, or they have changes in the NMR parameters, and I use the word parameters because intentionally, not because it includes not only chemical shift but also intensity of the signal and intensity of signal with reference to negative NOE or positive NOE. So not only chemical shift but also the intensity of the signal of those particular ligands which are affected are the lead candidate. They are the one. So for example, I have alpha glucosidase inhibitor, okay, and I throw in this particular medium in which I have an enzyme 10 different compounds, 10 different ligands, and I discover that two of them are tightly binding because they have enhancement in intensity of the signal and change in the chemical shift. I would say these are my lead molecule, and you can do it in a quantitative manner. So this will give you a whole profiling of binding, from weak binding, from no binding to weak binding, or weak binding to strong binding, just by looking into NMR parameters, intensity of signal, chemical shift changes. Okay, है ना interesting? That is, मैं कहता हूँ तो कहते हैं हाँ. God. It's not. It is. Okay, thank you. Okay. So, what we do, one particular, and this was a science paper. This was the first science paper, and remember, somebody publishing in science is really doing something extraordinarily important or has a relationship with the editor, right? Which is also an important thing, Knowing an editor and developing a permanent relationship is itself a skill which certainly deserves publication of his paper or her paper. Okay, anyway, forget it. I would like to invite you to think of developing a fragment-based drug discovery, so-called fragmentation expansion, so-called fragmentation linkages. Fragments are developed into more potent compound by using fragmentation expansion, linking, merging, tethering fragments together. Red and blue represent fragments which bind with the target protein, and these fragments are then linked together to produce high affinity ligand lead molecule. And remember, every time you go back to chemistry laboratory, yes, I think it's important. This is an important question. Now, I want you to answer this. You have a library of compound, okay? And these library of compound are screened against a target by using the same technology, so-called ligand-based NMR spectroscopy, and then you discover certain ligands which are binding with the active site. Now, question is that the content of knowledge has increased. You know, always remember there is a direct relationship between wastage, indirect relationship, inverse relationship between wastage and knowledge. When you would have more knowledge, you would have less wastage. अगर आपको आटा गूंदना आता है ना कि knowledge है, अगर हमें चलो सबको आटा गूंदना आता है तो आपका wastage उतना ही कम होगा, right? Even for making a bread, if you know how to make it, you would have less wastage. Exactly the philosophy works here also. Here the knowledge of active site is so prominent and so evolutionary developed that you would not like to have a random screening of lots of compound. Why you want to do that? Why don't you really have fragments which in your opinion would have the capacity of binding with the active site residues and then link them together, isn't it? So it is a knowledge content. When the knowledge content increased, then you start developing a knowledge-based drugs. So this is a knowledge-based drug. As you do with the in silico screening also, when you know the structure of a receptor molecule and you know the receptor, the structure of the active site, you can design molecules in silico, not in reality, in silico, which can bind with the active site. And then you go back to the library, you go back to the laboratory, you go back to your chemical lab and you synthesize that molecule in order to prove the hypothesis, is proving the hypothesis. This is a logical way of developing drug, is a knowledge-based, rational way of developing a drug. You don't start with thousands of compounds. You start with common 5, 6, 7 fragments, right? And then you link them together, the one which are more prominently binding with the active site residues also. You expand it also. For instance, here you see that you have expanded the molecule. You have you discover that by expanding means adding. For instance, if it is just a naphthalene, adding another let's say tetrahydrofuran into it would means that it will be more tightly bind with it. It's not a generalization, it's just a thinking that when you have a binding affinity determined, you would know what need to be done to improve the binding affinity on the basis of the knowledge of active site residues. Okay, so that's how you optimize. This is the reason why you optimize and then how you develop a molecule. So for instance, in this case, I've shown you a process in which you can have several fragments. Two of them were found to be interacting with the active site residues, and one of them was grown by using a chemical method because it was not so tightly binding. So you further grown the molecule. And you know how to grow the molecule. You add rings, you add chains, you do whatever. and then you link them together. You link them together. This process in chemistry is called tethering. Linking, tethering, Theating, tethering. So that process which links different fragments together are the process of tethering, and this this particular optimized drug molecule is actually a knowledge-based molecule. Now, I have discussed two things. I've discussed that you can have lots of lead molecules and you can screen them by using a very simple method called in which you have the chemical shift parameters of the ligand molecule determined. You can do structure activity relationship by NMR spectroscopy also, but before that I showed you that not only ligand but only the fragments are also can be linked together. So there is a chemistry involved, there is a high throughput screening involved, and now I want to take you to structure activity relationship by NMR spectroscopy. Identification of ligand with high binding affinity from library of compound by using a 2D proton N15 heteronuclear single quantum coherence technique. Remember, this is a proton detected technique. Kindly recall, it is a proton detected technique, is a heteronuclear technique in which you have proton and nitrogen interaction. Proton and nitrogen interaction. Remember, nitrogen are the component of all enzymes because all enzymes are proteinous in nature. And proton is component of your organic molecule. So if you can develop this interaction by heteronuclear single quantum coherence, you would know that the binding affinity, optimization of ligands by chemical modification. So now you know that the affinity of your lead molecule, you go back to your lab and you do a chemical derivatization. You add OH, you remove carbon dioxide, you do lots of things. I don't know whether I've really ever discussed with you the so-called minimum pharmacophore approach. I like this approach very much because lots of molecules which you see as a drug are not required to be in that shape. Only a small component of the molecule is pharmacophore, and therefore you just need to shed. You just need to break the bond. You need to get rid of the unwanted portion of the molecule. Exactly in the same philosophy, you can build the molecule. You start with a small molecule and you slowly add functionalities in it in order to improve the binding affinity. So it's a quantitative measure. It is a cycle in which you actually function. You have a binding affinity of a molecule, you go back to laboratory, you add OH or carbon dioxide or N-methyl or SH or whatever, or you make it a salt or whatever, you go back to the same NMR, you bind it with your receptor, you record HSQC, heteronuclear HSQC, you said binding affinity has improved. Binding affinity has improved. And you go back to the cycle because what is your ultimate gold standard for a lead molecule? Your gold standard is picomolar IC50 values. If you have, kindly remember that if you have millimolar IC50 values, you can imagine how much you need to have in order to treat a person. Right? You would need at least half a kg of a drug, which person would eat. So you need to have an extremely potent drug in a picomolar quantities, and few milligram of that drug should be sufficient to have a biophysical manifestation, so-called drug effect in a person. So in order to achieve that, you keep optimizing the whole cycle one after the other. So re-optimization of ligand by chemical modification. And as I said, that you can also line the ligands with appropriate linkers and check the affinity again, so you can do that. This is one example for instance, this is your receptor molecule. and this is your first ligand. Okay, so you identify a first ligand. You identify a ligand out of many ligand which was binding into the active site. Okay, and remember this has nothing to do with the enzyme function. You're not determining the enzyme function, because in order to have enzyme function modulated, the whole active site need to be blocked. So you're not doing it. It is beyond that. It has nothing to do with the enzyme function until this stage. What you are doing right now is just discovering the type of molecule which can interact with a part of the active site or a whole of the active site. Okay, so for instance, this active site, you can have more than one active site also. Peripheral active sites, the active site 1, 2, 3, 4, 5, you can have so many of them. Remember, the active sites are not necessarily the active site where a physiological reaction takes place, because substrate goes, normal physiological substrate go into the active site, but in order to open that active site, you may have a peripheral active site where a molecule interact and open the active site for the substrate. So there are plenty of different sites in this complex protein which need to be affected in order to have drug-like character. So for instance, in this case, you discover that this particular pink fragment is interacting with active site, and then you optimize this ligand. Optimize this ligand by knowing that this has a gap and a void, that you have to further expand this ligand by adding certain functionalities of carbon chain or an aromatic ring. And then you screen the second ligand also. Now you take out lots of ligand and you discover that the second active site or a peripheral site, there is a ligand which interact with the active site. And remember, you are doing it every time by measuring the chemical shift and intensity of the signal. Nothing else. Kindly remember that NMR can give you only the proton and the chemical shift and intensity of the signal. NMR cannot give you anything else. NMR cannot give you IC50 values or nothing like this. Everything else, any inference on the basis of NMR is drawn on the basis of the chemical shift and the intensity of the signal. More intense, more interaction, more NOE. Chemical shift modulation from one to the other, you can translate it into a quantitative terminologies, right? But the parameters on the basis of which you actually discover that your ligand is actually interacting with the protein molecule or receptor are the chemical shift. Chemical shifts of either ligand or chemical shifts of receptor, depending on your own choice. For instance, you have a second ligand and you discover that this ligand need to be optimized, and that means that you actually further grown this by linking. Okay, then you optimize the second ligand, and now these ligands are linked together. They call tethers. They have been linked together with several carbons. So this become a single molecule. This become a single molecular entity. Initially there were two fragments which were optimized, grown, and then you link these fragments together into a single molecule which is strongly inhibiting the function of the enzyme. This is the stage where you calculate the IC50 value in real mechanism-based assays by using a biophysical method. Before that, you were not worried about the function of enzyme. The only thing which you were doing is doing a pure chemistry. It's nothing but a pure chemistry, determining the structural component which gives you maximum non-covalent interaction, high binding affinity, mode of interaction. And this is the stage where you actually check the function of your inhibitor in real mechanism based in vitro assays, where you go to the wet lab, You find an enzyme, you add this enzyme, you go to the ELISA reader, you calculate percentage inhibition, and later you calculate the IC50 values. Okay. Very interesting. Now, in this whole paradigm of the application of NMR spectroscopy for lead generation, lead identification, and lead optimization, one technique which has attracted the most attention is STD-NMR, saturation transfer difference NMR spectroscopy. People write it in a very different way also, saturation transfer diffusion NMR spectroscopy, which is essentially the correct terminology, but I would like to call it as a saturation transfer difference NMR spectroscopy. Because, and I tell you the reason why I opted for a particular terminology. STD NMR spectroscopy is a very robust technique. It is an extremely interesting technique, a very valid technique, and it is now extensively used in understanding the mechanism of interaction, in identifying the component of the molecule which are interacting. Remember, your ligand is a large, your receptor is a large molecule, and your ligand is a small molecule. But in this a small molecule and a large molecule, there is a structural complementarity. There are certain features which complement each other, and when they complement each other, that is become the best fit. And that is how, thank you so much, that is how the affinity develop. But always remember that in your drug molecule, in your ligand, it's not the whole molecule of the ligand which is interacting with the active site. There's only a small component of the ligand which is interacting with the active site. It doesn't really mean that you shed all of rest of it, because always remember that the molecule need to be transported to the active site. It must have a solubility, it must have a permeability problem, properties, it must have an adsorption capacity, it must have an absorption capacity, it must have physical properties which take this molecule to the active site. So, assuming that only few atoms which interact with the active sites are enough is a wrong assumption. But because your molecule need to be transported to the active site also, and the molecule requires a hydrophobic interaction, hydrophilic interaction, so-called lipophilic interaction, or so-called amphipathic interactions, a whole range of different interaction. So the part of that molecule which interact with the active site is called epitope. Part of the molecule which interact, part of the small molecule or part of the ligand which interact directly with the active site is called epitope. And this STD NMR spectroscopy is called epitope mapping. You want to map, you want to understand that which part of the molecule is actually interacting with the active site of the receptor or an enzyme is an epitope mapping. This is a very interesting and a very important technique. And technology, the whole concept is very, very easy. What do? You selectively saturate, and I'll take time, don't worry about, you can ask me questions whenever you want. Selectively saturate receptor. Selectively saturate receptor means that you need to have a pulse which selectively pre-saturate protons of a receptor, like protein, right? Okay? Or viruses, or a hormone, whatever. Generally in the region where ligand has no proton. is important. You want to saturate selectively the protein protons, right? So you select a region in which ligand has no signal. Ligand has no signal, right? If ligand bind with the receptor, saturation will propagate within the protein and eventually transfer to the ligand. Okay? And then this saturation transfer will increase or decrease the intensity of the ligand, epitope, not the whole molecule, only the epitope. And let me take you to, okay, this is a very nice diagram which I have taken from a research paper. This is a receptor, this is your protein, and what you're doing that you're selectively irradiating protein signals. Okay, protein signals. So you give radio frequency pre-saturation oscillator fixed on certain protons of the protein, right? Now, there are two different candidates for the active site. This is one candidate and this is the second candidate. You put them together along with the protein. What will happen that this energy which is given to certain protons of the protein will propagate in the whole protein by a phenomena called spin diffusion. The energy would not remain in those protons, but in fact this would propagate in the whole protein. And when it will propagate the whole protein, and at a certain point of time when it reaches to the active site, this energy would eventually transfer to the ligand. If it is binding and if it is close to, अभी मैं check करके देता हूँ. And if it is close to the active site, if it is fitting in the active site, part of the molecule is not the whole molecule, it is the epitope, right? It is part of the molecule. And remember what will eventually happen, that this ligand molecule in the binded form will receive energy from the protein by a phenomena called nuclear over-Roger effect. When they are close in space, less than 6 angstrom, they will receive energy from the protein by a process called cross-relaxation, nuclear over-Roger effect, whatever you want to name it. And then you would be able to see the change in the intensity and chemical shift of ligand proton. You would see no change in it because it is not fitting with the active site. Okay? So this is not a ligand. It is just a molecule which is so strange to protein. It is not interacting with the active site at all. Only that particular molecule which is receiving the energy from the active site, pre-saturation from the protein, and having change in the NMR parameters like chemical shift and intensity are the true ligand. And this is called saturation, transfer, difference, NMR spectroscopy. Epitope mapping. This whole ligand is not receiving the energy. Only that part of the ligand is receiving the energy which is in the active site. Remember I versus S in NOE. Only I, when S is saturated, the I receive energy, not the whole molecule. Only those protons which are close in space, less than 6 angstrom, receive energy from the protein by nuclear over-Roger effect or cross-relaxation, and these are the epitope. This is the part of the molecule which is called epitope, and the whole process called epitope mapping. This is the only technique. This is the only technique other than X-ray crystallography in which you can identify the epitope. In X-ray crystallography, you have a co-crystallization. In X-ray crystallography, you crystallize your protein along with the ligand. And when you do the X-ray structure, you know precisely which part of the molecule is in the active site. You get a photograph, right? So other than X-ray crystallography, this is the only technique which will give you a direct mapping of the epitope. Extremely powerful, very, very robust technique. Great future of NMR spectroscopy because it is now used for mapping of the epitope. Remember that two things are happening at the same time. Number one, that you have identified a useless molecule. Number two, you identify a useful molecule. Number three, you also identify part of the molecule which is in the active site. So that several important mechanism-based informations are obtained by using NMR spectroscopy in drug discovery and development. Okay? And that also gives you a pharmacophoric group. So for instance, if you say, I discover that this ligand has an epitope which goes into the binding site of the enzyme, and I want to get rid of this. कौन सा color होता है? Eh? Light purple, or this is red. Pink, this is pink, sorry. I don't know the colors. So you say that I want to get rid of this particular rectangle. I want to get rid of this particular part of the molecule because in my opinion, it is not really helping. Okay? And if you just dissociate, if you just break this, and if there is no change in the NMR parameter, you should be happy that you got rid of a part of the molecule which is not contributing in the druggability. But if it decreases, then you cannot do that. So you keep trying by optimization. Why it is important to have an optimized drug, not a very large drug, if it is not necessary. You remember the structure of artemisinin? Artemisinin is a large structure. Only that part of the molecule which has a diepoxy ring, right, is a pharmacophore. And the whole artemisinin can be chopped out and a new molecule was developed, which is called artemether. And this artemether is nothing but this diepoxy containing 6-member ring and another 6-member ring next to it. Why you want to do it? Because if this part of the molecule is not contributing in any way, physical properties, absorption, adsorption, cell membrane permeation, in any way, if it is not contributing, it is useless to have it because it costs money to incorporate that into the structure. Okay? So you want to have an optimized minimum pharmacophore. It gives you this ability of manipulating the structure and then rechecking it. So epitope mapping is then grow into a process called lead optimization. Amazing technique, a very, very interesting technique. And oh yeah, sure, absolutely. Thank you for asking me this question. You can also have an exchange spectroscopy in STD mode, in which you can also determine that. Remember, your ligand is never fully binded with the receptor. It is always in equilibrium with non-bound and a binding form. If it is more in binding, it is a drug. If it is less of binding, it is not a drug, right? So this idea of the dynamics can also be measured by using by using a spatial STD sequence जिसको लोग use करते हैं in a time dependent manner, and STD in XC mode, EXSY, STD with EXSY, which is exchange spectroscopy. Okay, so I want to take you back to the whole thing. Selectively saturating a resonance of receptor protein in the region where ligand protons do not have any proton, such as 0 to 1, but not necessarily 0 to 1, because there are certain ligands which have proton in this region. How you would know that you should not irradiate between 0 to 1? How you would know that you need to irradiate between 2 to 3 or 6 to 7? How you would know? How would you would know? By proton NMR of ligand. Proton NMR of a ligand will tell you where not to saturate. है ना? And other than that, protein, I would never go beyond 7, 8, 9. Because I don't think there would be many protons in that region also, except the one which are hydrogen bonded or whatever. But I would be very happy to go upfield, even to 0 to -1, because I know that in a protein structure, there's lots of protons which are in this particular region because of magnetic anisotropy, because of the shielding effect of that. So generally the irradiation is done between 0 to 1. Between 0 to 1. You know why 0 to 1? Because the molecule which have anything in 0 to 1 are generally lipophilic. They are hydrocarbon containing compounds. Anything which comes between 0 to 1 are hydrocarbon, methyls, etc., etc. And they are not drugs, believe me. Generally drugs जो हैं वो anything which comes in hexane or pentane or पता नहीं क्या क्या, they are generally not drug. They can be fragrance, they can be khushbu, they can be perfume, anything, but they can't be drug. The drug needs to be somewhere between 3 to 7. Lipinski rule, remember? Hydrogen bonding, hydrogen accepting, rotation, butanol, water, diffusion coefficient, other thing. Okay, so once you do that you irradiate a part of the receptor by using a Gaussian pulse, a shaped pulse, then you would be able to see where the ligand bind with the receptor when saturation will propagate from selected proton to the other protons of the receptor. ठीक है? Within the protein you would have propagation of this saturation, and that is a phenomenon called spin diffusion. ठीक है? The saturation is then transferred to the epitope of the ligand, which is in the active site. Okay? And that change and that transfer of saturation will eventually manifest as change in NMR parameters. For instance, chemical shift changes or intensity changes. That will tell you the part of the molecule which is in the active site of the enzyme. Okay. ये क्या हुआ है? Ligand bind with receptor control experiment is run. Now this is important. I want you to add something else also. Control experiment is run by saturating a region in which you don't have any proton or protein and a ligand. Interesting, nahi? Remember, you're recording the NMR spectrum of ligand by a normal pulse sequence. In addition to that, what you are doing, you are actually you are actually saturating the protons of protein. If you irradiate in any other region which has nothing to do with the protein, there would be no absorption of energy into protein. And when there will be no absorption of energy of the protein, there would be no transfer of saturation or NOE to the epitope. Right? And this is called off-resonance saturation. Number one was in-resonance saturation, in which you had certain protons of the protein, and then it's called in-resonance. And there is a technique, there is a control. जैसे control होता है ना in experimental designing, this is a control in which you are irradiating a region which has no proton of protein. Nothing. Then the ligand proton will come without any change. Right? In the first experiment, the ligand proton will come with change. Right? And the other experiment, the ligand proton will come without any change, because there is a no saturation transfer. A very important point है. In first experiment, you saturated certain protons of the protein, which eventually transfer to the ligand by a cross-relaxation by NOE. NMR spectrum of this particular experiment would have changes in the parameter of ligand molecule, ligand protons. In an experiment, which is a control experiment, you irradiate a region in which there are no protein protons. When there are no protein protons, the protein would receive no energy. And when it will receive no energy, it will not transfer any energy to the ligand. So the ligand proton would appear as they are. And if you minus this from the first one, you would get what? But what? What difference? The change in parameters because of the interaction. Change in parameters because of interaction. That is the reason why it's called saturation transfer difference NMR spectroscopy. Very simple. One is called in resonance pre-saturation of protein. Okay? The other is off resonance saturation of protein. It means no saturation of protein. The difference, what you are recording is a ligand. The difference between the two spectra are the difference because of the interaction with the, and you do it several cycles, you do in resonance, off resonance several times. In order to firmly establish this experiment, you do in resonance experiment in different regions of protein, and do off resonance experiment in different regions also. But at the end of the day, what you get is that this is, okay, this is the pulse sequence. This is a pulse which is called Gaussian shape pulse, and this is the heart pulse on proton NMR for ligand protons, and you then have a reduction. And what you are detecting is the following. You see, this is your ligand. Okay? This is your ligand. This is your ligand receptor complex. That's how you are in resonance saturation, carrying out in resonance saturation. Region of the protein, chemical shift of the region of the protein. You pre-saturate. As you pre-saturate, this energy propagate in the whole of receptor molecule by a spin diffusion phenomena. And then a part of this energy, based on the NOE, nuclear over Auger effect, closeness in space, They are close. That's why they are affecting right at the active site. Then you would see the difference in the NMR parameters. And then you see that the NMR parameters of this particular part of the molecule are affected only, not these. Okay? Only this particular molecule part is called epitope. This is an epitope, right? And this is an epitope. So this is a reference spectrum, a control experiment in which there was no proton of protein. This is your NMR of ligand. Then this is a selective, this is the NMR of protein. Let's say 4 और 5 के दरमियान बहुत सारे protons होते हैं. Between 4 and 5 you have lots of protons in protein. Alpha proton of every amino acid comes between 4 to 6, right? So when you irradiate that particular region, then you would have a NMR of a ligand. If you minus this from this, you get difference. And this is called saturation transfer difference. This is a control experiment in which irradiation was done nowhere, and this is an experiment in which saturation was carried out on protein. And when the saturation was carried out on protein, then you had this phenomena of saturation transfer. And when there is a phenomena of saturation transfer, the intensity increase. And intensity increase because of what? NOE, W2, W0, please kindly remember, right? It can be negative also. Please remember that it can be positive and it can be negative depending on the viscosity of the whole solution. Assume that it is positive. When it is positive, you see the intensity increase in signals. And when you minus this spectrum with this spectrum, you get an STD, saturation transfer difference. And this difference is a quantitative measurement of binding affinity. Okay? If you have more of it, it is more closely bounded. If you have less of it, it is less closely bounded because it is done in a transient NOE manner. Okay? If you have a negative NOE, you would have a negative signal appearing. And you would know that they are also interacting. So negative NOE and positive NOE both means interaction. The only difference is that in one case, W2 is operational, and in the other case, W0 is operational. In a less viscous solution, you would have W2 operational positive NOE. And in more viscous solutions, you would have W0 operational and negative NOE also. I want to ask you a question. Why there is no change in chemical shift? Because it is already binded with it, you know. It is already binded. What you are measuring here is the increase in intensity because of saturation transfer. Okay, a very neat, beautiful technique. Any question? You can do it from the other side also. There are two different ways of doing it. You can do this also from this, and you measure the proton of protein. But there are lots of disadvantages. You see, protein is always taken in a nanomolar quantity, very small quantity. In that case, you would be recording a protein NMR spectrum. Remember? You don't want to do it that. You want to rely on a small molecule. Okay? So although protons are visible here also, but they're so small, little, as compared to ligand molecule that you hardly recognize them. And that is the reason why I didn't really show any signal of this. Although signals are there. Protein NMR, proton would not go anywhere. They would always be there, but they are so less as compared to the concentration of the ligand that you would not be able to see them. Okay? So this is the reason why it is done in a different manner. It is done in an easier manner in which you saturate the protein and you record the STD on this. We have already discussed. Huh? Any question?
Sir, why there were 3 peaks?
I don't know actually. 3 peaks actually belong to this gola. It means there are 3 protons which are close to this particular. It can be 6, 7, 8, 9, 10. Okay? Why difference in this? Yes, there's an interesting question. Okay, assume that there are other protons also. Assume kar le, there are other protons of this. Is a oversimplified version. And please remember that the other part of the protons of the ligand are also available. They also give the signals. The intensity of only those signals increase in size which are in the active site. And why they are increased in size? Because of NOE. Remember nuclear over Rosser effect. They are close in space, less than 6 angstrom, very close to the protons of protein, and protons of the proteins are your S, source of energy, and the protons of epitope is your I. Interesting, or the one which you are discussing. Okay, so that is how you see the intensity increase is because of the NOE enhancement cross relaxation, and that is the reason why I wanted you to actually understand that once we have discussed the NOE difference NMR spectroscopy.
Sir, pharmacophore and epitope are same.
Pharmacophore are pharmacology का term है. Pharmacophore is part of the molecule which is essential for the pharmacological activities. But epitope is not necessarily the whole pharmacophore. It can only be a part of a pharmacophore. Right? Epitope is just a particular part of the molecule or a pharmacophore which are actually binding with the active site. And remember, when I say binding, it means non-covalent binding. Because once you have a covalent binding, nothing like this would happen. This would probably happen, still happen, but this become a one molecule. You see, if ligand bind covalently with the receptor, they become one molecule, not 2 molecules, right? So in the whole drug discovery, you are looking for non-covalent interaction because that is your drug. If your drug bind with the protein, then it's not a drug. It's not a drug. It becomes part of your body, right? You don't want to do that. You want a drug and you want to excrete the drug in a very short span of time. Half-life of more than 1.5 day is not a desirable thing. Always remember, if a drug retain in your body more than 1.5 days, it is a dangerous drug, right? This is the reason why you are developing techniques for sustained release of drug. You are developing particular myceliums, nanoparticles, whole range of different things which you impersonate in body and they are slowly releasing the drug with time. Okay? So lots of interesting things. The whole philosophy of absorption.
Sir, same thing that in chemotherapy, like in anti-cancer drugs as well, we need the non-covalent binding drug to the receptor or the covalent.
You see, in chemotherapy, of course, you need something which excrete out of the body. You don't want to retain it into the body also. That is the chronic deposition is a major problem. In chemotherapy, everything is chemotherapy. Chemotherapy in cancer is cytotoxicity or immunomodulatory activity of a particular compounds against cells. And that cells are normal cells and cancer cells also. Why they are absorbed more in cancer cell? Because cancer cells have a high metabolic rate. They have a very high, several fold more metabolic rate as compared to normal cell. These chemotherapeutic agents would have a target. They are not killing the whole cell. Kindly remember, nothing can kill the whole cell unless you have a small nanorobot which start scavenging. It has a target, it has a target, maybe cell wall, or a particular enzyme which is responsible of further division of these cells, or an enzyme which increase the rate of apoptosis, or an enzyme which go into the mitochondrial cycle and disrupt ATP energies. So you can have plenty of different types of targets of chemotherapeutic agent, but they would always do their function and excrete out of the body. They would never bind with it, because if they remain, then you have a whole system of so-called glucouronidase, the whole cycle in which waste material is taken out of the body. Okay? So this is, and I want to give you example of very exciting work which was conducted by my student Dr. Arif Lodhi and Ajmal, and that is an example of Helicobacter pylori. As you all know, Helicobacter pylori they are the causative agent of peptic ulcers and gastric ulcer and gastritis. And these were the molecule which we discovered that these are the compound which were synthesized by Professor Dr. Khalis group. These are biscoumarines, and there were many natural compound also. So we initially work on natural compound, and we discovered that these biscoumarines with glycoside, C-linked and O-linked, they are capable of binding with the urease, and eventually we decided to synthesize the libraries of compounds. So these libraries of compound were synthesized different from each other by a factor of R. Then this is almost like 30 or 40 of these compound, and then then this work was conducted by Arif and Dr. Zahid together. These are 30 overlap biscoumarines. So you see the only orientation change is particular R. Remaining biscoumarine part, aromatic part are almost overlapping. So the assumption was that this particular part of the molecule is interacting, the lactones are interacting with the active site. And the whole philosophy was based on the fact that urease is a bi-nickel compound, bi-nickel enzyme which has two nickels. And between the nickel there is a water molecule and a carbamate. And anything which can slice between the two nickels will disrupt the function of the enzyme. And most of the urease inhibitors are sulfur and oxygen containing compound. Disulfide, thioureas, and a whole range of different compound with oxygen double bond, sulfur double bond, which are capable of forming a complex with the nickel atom. So what was the assumption? Assumption was that if this lactone is active, then we should be able to see the increase in intensity by STD of 8, 7, and 6, which are close to this. And that precisely happened. This is the STD NMR spectrum, and this proton. So the difference spectroscopy, urease was irradiated. A part of the urease was irradiated. A control experiment was conducted. Difference spectrum was taken, and then we identified that there are certain protons which have increase in intensity. Remember, this is just an increase in intensity. The other protons which are not receiving any saturation are totally disappeared because difference, na? So this is just an intensity increase, and these are two protons, and eventually these are three different protons, this is 6, 7 and 8. These are the three protons which are part of the molecule. What we have discovered by doing this, we know that it's not the R part of the molecule which is interacting, but only the lactone part of the molecule is interacting with the active site, which is bimetallic site, contain 2 nickel. And we know precisely that that this part of the molecule is interacting and not the R which is interacting. And this is the reason that the despite of different R's, the activity is more or less the same. It's not so different. Okay. Anything else? कोई चीज very exciting lecture, huh? Sorry, discussion, no lecture. I don't believe in lecturing. We don't saturate the active site at all. We just saturate any part of the protein. Just few signals. You just saturate by a Gaussian pulse, a train of pulses, right? When you saturate, the energy is pumped into the protein. And then it diffuses within the protein by a phenomenon called spin diffusion. And as the energy goes all over the molecule, all over the protein, it eventually reaches to the active site also. And then when it reaches to the active site, just close to the active site, just a distance, just so geometrically close is the epitope of your ligand. And this epitope of your ligand is receiving the energy by a cross-relaxation nuclear arousal effect. As a result, you see the intensity of the signals of epitopes increase. And this is called STD. So I have actually taken through, there are lots of other NMR technique also, but these are the most important one. Ligand generation, when you have several ligands, you put them together into a receptor and you see which ligand is interacting. Fragment based interaction, which you have fragments and then you link them together and you optimize. Then you can use it by optimization of your lead molecule. And you can also use this technique for epitope mapping by using saturation transfer difference spectroscopy. I also told you that this process is a quantitative in nature, and the intensity of peak will tell you which particular molecule is interacting strongly, high binding affinity as compared to the other. You would be pleased to know that results of epitope mapping by STD are 99% often correlate, is a very high proportion with the IC50 values. So the one which come close to the high affinity generally give a very low IC50 values. The one which has less of saturation transfer generally have very high IC50 values, okay, in micromolar. So it correlates very well with, in fact, the correlation of NMR-based structure-activity relationship is very, very well established as compared to in silico screening, because in silico my prediction can be entirely wrong because confirmation can be very wrong also. This is a real NMR, this is a real experiment in which you have a receptor and a ligand, real experiment. You have two different detection systems. In this, you are using NMR as your detector. In the other, you are using a chromogenic spectrophotometric method. Therefore, both would give you exactly the same result in principle. Yes? You see, in principle, you can do it only once. You see, and you need to, it's not a short pulse, it's a pre-saturation. It's a broad pulse, right? So you pump lots of energy into the system. But in order to cross-validate that it is really a real STD and not a false STD, you do it several times in resonance of resonance by selecting different regions of proteins. by selecting different regions of proteins which are not in the region of ligands. Always remember that if you irradiate in the region of ligand, you would get nothing. Right? Okay. Anything else, please? Is it exciting? Anna? Well, this is the first time actually, so for me it's also a learning experience, but I was very excited. I went through lots of paper, and I was so happy that I could absorb at least part of it. Okay. Yes. Oh yes, SCD is now available in 2D NMR spectroscopy. You can correlate the NOE, increase in NOE with time, increase in NOE, proton-carbon connectivity, proton-nitrogen connectivity. हमारे पास कौन सा है? We have a 2D?
Yeah.
We have a 2D.
But first we need to check 1D. If
1D.
there is nothing in 1D,
Then you don't go for. Remember why you need to have 2D? Please remember that you are actually measuring the rate of building up of NOE. Okay. Any other question? Anywhere else in Pakistan? Okay, thank you very much. Tomorrow, Dr. Atia will have a discussion session on biological NMR spectroscopy, because I have a meeting tomorrow at 2:30. The lecture would be right at the same time, but you would be learning more about biological NMR spectroscopy, protein NMR spectroscopy. Thank you. Thank you.